So, to the best of my memory, I discussed about what was observed by IMB and Kamiokande. Both experiments were set up to search for proton decay, and neutrino interactions are actually background for them. And they saw that this double ratio R it should have been 1, but they measured it to be about 0.7 or so. I don't remember the error bar, but it is small enough that error bar is small enough that this ratio is established to be definitely less than 1. And then there is also the up-down asymmetry. That is number of upgoing muons minus number of downgoing muons divided by number of by the way, sometimes instead of this people also just take up-down ratio. Of course, one can trivially convert one into another. Thing of course is, if n mu equal to, if the numerator and denominator are very close, this is 1 but this is 0. So depending on what the value is, you would choose one ratio or over the other. But in this case, this ratio deviates enough from 1 so that some people find this ratio to be convenient and some people find this ratio to be convenient. So, and so if there is nothing new, this should have been 0 and this should have been 1, but there is enough deviation from that prediction that it was established. I shouldn't say it was established because there were enough number of skeptics, but there was a very strong hint that at the muon neutrinos produced in atmosphere, they are doing something beyond what we would naively expect from standard model. So obviously, when there is such a mystery, you want to solve it, and to solve it you need a bit better detector. Ideally, of course, I think I told you IMB was a detector in US and Kamiokande was a detector in Japan. And ideally, of course, both groups wanted to build bigger and better detectors. But there was some funding crunch, so the two groups suddenly, who were severe competitors till then, suddenly decided to become collaborators and combine their forces and came together to build Super Kamiokande. Kamiokande size is something like 8 to 10 kilotons. I don't remember the exact number. but Super Kamiokande was a 50 kiloton detector, out of which half of it was the fiducial volume. What is fiducial volume? That's actually a slightly different thing. We will talk about it sometime later, but for the moment, this Super Kamiokande was built, essentially involving the people from both IMB and Kamiokande. By the way, coming back to IMB and Kamiokande, as I mentioned earlier, they tried to look for proton decay, and in their search for proton decay, the neutrino interactions actually was a nuisance for them. They didn't find proton decay, but they ended up finding neutrino oscillations or atmospheric neutrino oscillations. There is a famous comment by Fermi that yesterday's discovery becomes today's calibration, to which Feynman is supposed to have added, it will become nuisance factor in tomorrow's experiment. But here is where the nuisance factor actually became the discovery.
So you said half of 50 kiloton is fiducial volume?
Yeah, actually a little less, 22.5. And IMB used phototubes, and I believe they covered, I don't know, something like 10% of their surface was covered with photomultiplier tubes. I mentioned that Kamioka wanted to do one better, and so they built special photomultiplier tubes, bigger ones, with which they could cover 20% of their surface area, and that allowed them to detect lower energy charged particles, so they could actually see signal for solar neutrinos, whereas IMB had no solar neutrino program. So based on the experience that was gained by running IMB and Kamiokande, Super Kamiokande tried to do the best job they could, and they actually had sort of super big photomultiplier tubes which covered 40% of surface area. It had two purposes. One, of course, is sensitivity to low energy particles, in particular low energy electrons or positrons. And second is better reconstruction of the direction. So you have the Cherenkov light that is being emitted by the charged particle, and the better you are able to reconstruct the Cherenkov cone, the better is your ability to reconstruct the direction. And we will soon see why that is important, and that is also illustrated in that paper of John Leonard, where the direction, the better direction reconstruction, that was the one of the most crucial advantages that Super Kamiokande had over IMB and Kamiokande.
Why better sensitivity to specifically electrons, positrons? Low energy.
So that you can see solar neutrinos. Okay, let me handle that question first. See, this is, if you look at the flux of atmospheric neutrinos, and let's assume both are log scales. It is roughly a straight line, with a slope of minus 2.7. So, flux falls off very sharply with energy. This is true of cosmic rays also, and this is reflected in atmospheric neutrino fluxes. So, you have very high fluxes at low energies and low fluxes at high energies. Now, in the case of mu, there is a kinematical limit. You need E nu greater than 100 for you to produce the muon. But just above this kinematical limit, the muon is non-relativistic. It will not produce Cherenkov light. For the muon to produce Cherenkov light, it should have a momentum of, it should have kinetic energy of about 100 MeV. It should have a gamma factor of about 2 before it can produce Cherenkov light. So, you have that as far as muon detection is concerned, you have a lower limit of 200 MeV. And atmospheric neutrinos are coming from all over the place. But in the case of electron neutrinos, to produce an electron or a positron, I need energy of only 0.5 MeV or so. Okay, then there are nuclear levels, but something like 2 or 3 MeV neutrino can produce an electron or positron. But the flux of those is huge. And second is they are coming from all directions. And these electrons and positrons are coming from all directions. And some are relativistic, they produce some Cherenkov light, some are non-relativistic. So, if you try to catch all of them, then you really can't make head or tail of what is happening in your detector. So, you need to put some threshold. And the threshold they have put is E nu E is greater than 100 MeV. As far as atmospheric neutrinos are concerned, they will consider only those signals with E nu E greater than 100 MeV. But in the case of solar neutrinos, the max E nu is 14 MeV, and the detection mechanism is this nu E comes and knocks an electron out, and this electron has kinetic energy Te, which is greater than some x MeV, and you have to sort of tune your detector so that you can catch this. So, but won't this, and let's say x is a number, let's say between 5 to 10. But won't this solar signal be overwhelmed by the low energy atmospheric signal? Answer is no. The reason being, the flux of the solar neutrinos is few orders of magnitude greater than even low energy atmospheric neutrinos. So, solar neutrinos, in that sense, they have a distinctive signal. I mean, you can be, and you know that they occur in that narrow energy range, 5 to 10 MeV. And so you look for electron neutrinos in that, electrons in that range, 5 to 10 MeV. Okay, there is some contamination due to atmospheric neutrinos, but that's maybe at percent level or maybe sub-percent level. So we don't have to worry about it. That is point number 1. Point number 2 is the directional information. So this is the sun and Earth is here. Well, actually, let me redraw it with the Earth to be big and sun to be small. So this is where my detector is, and so during daytime sun is here. So solar neutrino comes like this, whereas at night time sun is here and solar neutrino comes like this. So what I can do is, depending on the time of the day, I identify a section of my detector, and in that section of the detector I enable it to be sensitive to this 5 to low energy neutrinos, low energy electrons, and take data. So I have both the energy window, let's say 5 to 15 MeV, and also the direction window, and moreover the flux of solar neutrinos is orders of magnitude larger than even flux of low energy atmospheric neutrinos. Because of these 3 reasons, one can detect solar neutrinos. In fact, if you sort of look at, I hope all of you know, there's an experiment called RENO. It's a reactor neutrino experiment. It is headed, rather was headed for 10 to 12 years by a man called Subong Kim. Subong Kim was a PhD student in the same department where I was, so 2-3 years junior to me. And professors in our department, they were members of Kamiokande. I think they were the only US department who joined Kamiokande rather than IMB. And this is what Subong Kim did for his PhD. Study low energy electrons in the detector and sort of make a decision that this event, the likelihood of that event being due to a solar neutrino versus some other source. and that was the problem he and of course the group in which he was involved they solved, and they could construct an algorithm by which one can reliably say that okay, if you see, I don't know, 100 such events, you can reliably say maybe 80 or 90 such events are solar neutrinos, and that is what enabled Kamiokande to do a solar neutrino study. And in fact, Subong's thesis was something which was sort of praised very highly when he finished his thesis, because it made a sort of real breakthrough in terms of how to do solar neutrino physics with these water Cherenkov detectors. Yeah, and Kamiokande originally had something like X to be some 10 or 11 MeV. After a lot of hard work, they managed to bring it down to 9, but that was the limit. They couldn't bring it down anymore. Whereas Super Kamiokande design, they originally had 7 and then they lowered it to 5. So you got more signal, and also you are able to study the solar neutrinos as a function of energy from 5 MeV to 14 MeV, which had a very important consequence for fixing what the solution to solar neutrino problem is. So now, okay, let us discuss neutrino oscillations. So IMB and Kamiokande showed that muon neutrinos in atmosphere are doing something. So we assume that mu is oscillating into mu x, where mu x is either mu tau or mu sterile. We will assume that it's not mu e. This is actually a slightly simplistic assumption, but you can, why it is not mu e, one has to make a, let me step back. So to start with, we will do only a 2-flavor oscillation, so we will not worry about 3-flavor oscillations. So if mu is oscillating into mu x, then for mu x there are 3 possibilities: mu e, mu tau or mu sterile. Now, if it is mu to mu e, and of course backward also, because in atmosphere there is a nu e flux also, then you will find that muon neutrinos are oscillating into electron neutrinos, but electron neutrinos are oscillating back into muon neutrinos. Of course, initial muon neutrino flux is twice the electron neutrino flux, but which means that if you see a reduction in the muon neutrino flux, you should see an increase in the electron neutrino flux. So this implies that reduction in a mu must be accompanied by reduction in upgoing and mu must be by increase in upgoing and mu. And we find from super Kamiokande data that that is not happening. So this SK didn't see this. So rule it out. So that leaves, we have mu x is mu or mu sterile. But for
Sorry, x is nu tau or
mu tau or mu sterile. Sorry. For the moment, we won't care whether it is mu tau or mu sterile, because we are looking only at muons. So what is relevant for us is muon neutrino survival probability, and muon neutrino survival probability in two flavors is given quite simply by sine square theta sine square it doesn't care whether what it has gone to is sterile or tau. So the question we can ask is, the data seen by super K, does it match this prediction? And answer is yes. And first I'll explain things in a slightly in a algebraic way, and then we will look at the figures. So what super K observes is dn mu by d cos theta mu, and similarly dn e by d cos theta e, where theta mu is the angle that the produced muon makes with the vertical axis, and similarly theta e is the angle that the produced electron makes with the vertical axis. This is what is measured. So I should have a theoretical formula to compare with these measurements. And how does the theoretical formula look? What is my first ingredient? First ingredient is the flux of atmospheric neutrinos, and that depends on the energy as well as the direction. By the way, why should the flux depend on the direction? After all, I insisted that cosmic rays are coming isotropically in all directions. So why should the flux depend on the direction? This is actually something quite simple. It's because
get more time to decay.
it's because of the thickness of the atmosphere. See, the picture is quite simple. This is Earth and this is where my detector is, and this is the thin layer of atmosphere surrounding it. So a cosmic ray coming from here, it will encounter only about 10 kilometers of atmosphere. But actually the scales here are really bad, but what you should imagine here is the detector is like that. Now a cosmic ray coming like this, it will encounter a much thicker layer of atmosphere compared to a cosmic ray coming from above. So, and you put it in your Monte Carlo and do the calculation, and you find that the vertical fluxes are about half of horizontal fluxes. This is without worrying about Earth's magnetic field. If you put in Earth's magnetic field, you will, depending on the energy, these fluxes will also develop some dependence on the azimuthal angle. According to this, there is a perfect symmetry about this axis. So fluxes should depend only on the polar angle theta, not on the azimuthal angle phi. But the magnetic field breaks that symmetry. So there is also a dependence on the azimuthal angle phi. And that's why one has to run these Monte Carlos, and of course you feed in all the data you have taken from cosmic ray experiments and surface muon measurements, measurement of cosmic ray muons on the surface, that too at sea level, 100 meter, 200 meter, all the way up to whatever height. All these data you put in your Monte Carlo, and it will churn and will give you the. In principle, the phi dependence is there, but for simplicity, I am neglecting it here. So once the neutrino is produced, it has to travel, so the survival probability comes in, and this survival probability, as we see from here, it depends on E and L. And the L, the distance traveled by the neutrino, is a function of cos theta. So I'll put that in. And then how do you convert flux into event numbers? What do I need? I multiply flux by something to get the event numbers. What is that something? Flux is number of neutrinos per second per unit area. So I have to multiply it by something with dimensions of area to get number of events. Cross section. But the cross section varies with energy. So I should write d sigma d nu, which is actually d sigma d mu, but this is a function of both e nu and e mu. Actually, and there is one other thing I need to worry about. Just 1 minute. Actually, the cross section we don't write like this. We should write it in a slightly different way, so that I get this cos theta mu on this side. Times d sigma times e nu cos theta. And I integrate this over e nu and cos theta nu. Actually, I should put that is the angle between the neutrino direction and muon direction, cosine theta of that. That is the angle that comes in. And I have to integrate this over d cos theta nu and d nu. So now we match everything. This is number of neutrinos per time per area. Of course, there is a d nu d cos theta nu. This is just a number. I am multiplying area but per cos theta mu, but that is there on the left hand side, and I am integrating over d nu and d cos theta nu. So anyway, so an important input in this theoretical calculation is this cross section, which is actually the something that was not known properly. So people had to do a lot of extrapolations to make educated guesses about what this is, and I hope all of you know of this Monte Carlo called nuance, which used to do which we are still using for INO to do the event rate calculations in the case of no oscillations. And there's a man called Dave Casper who wrote that program, especially for Super Kamiokande, I believe. And if you look at nuance, the most complicated part of nuance is this cross sections, because there are people have developed atmospheric neutrino flux Monte Carlos, which are quite reliable, and of course calculation of the survival probability is reasonably straightforward. And this cross sections actually was the biggest stumbling block, and in nuance, for example, there are hundreds of different channels which are inputted, and to get as accurate a prediction of this quantity as possible.
There is another generator, Genie, right?
So
how is it different? Or
if you ask me what is the difference between nuance and Genie, okay, the very straightforward answer is I don't know. But my guess, first thing, nuance, to the best of my knowledge, it was explicitly developed for Super Kamiokande. So it was developed to calculate atmospheric neutrino event rates. Genie, I believe, was developed for a more general purpose situation where you can use it for any neutrino experiment. So what Genie, first, there's also sort of question of manual effort, so to speak. This Dave Casper took it on himself to get the best possible Monte Carlo he could design in early 90s. So he took the trouble to put together all the cross sections, prepared the tables, inputted them into the Monte Carlo. But then over the next 10 years or so, he kept, as more and more data on neutrino cross sections came, he kept trying to improve it. But at some level, effort was too much for one person. So, and also people realized that it has to be a community effort. So a Genie collaboration was formed, and of course people are coming in and out of Genie collaboration. And for example, Ali Ajmi, who did her PhD with me, but while doing her PhD, she and Professor Govinda Mazumdar, they have contributed something to Genie. So people can do such partial contributions also. It's a fully open source code. And the basic idea of Genie is to develop a Monte Carlo which includes all the neutrino interaction data that is available, so that you input whatever flux you want. It could be atmospheric neutrino flux, it could be an accelerated neutrino flux, or whatever other flux, and it will give you the event rate. It will give the predicted event rate for that. So, and then of course, to match it with your experiment, you have to then combine it with your detector efficiency. So, it's like, this is what you want, and the inputs you need are flux, cross section, probability, and detector effects. And the inputs that Genie has within it are the cross sections. And the external input it wants are the fluxes, probabilities, and detector effects. But I believe it is sort of written in block mode. So you just give the flux, and then it gives you the unoscillated event numbers. And you can include the cross probability in whichever way you want. And one simple way people try to do is this accept reject method. Instead of putting the probability into the Monte Carlo, we convolute the probability after the Monte Carlo output. Strictly speaking, that's not the quote correct way of doing it. But if you are Monte Carlo, of course, you are generating huge Monte Carlo samples for 100-year, 500,000-year exposures. So, in that large statistics limit, this accept-reject method gives essentially the same results. So, you impose the probability on the output of Gini, and once you impose the probability, then you impose the detector effects. Or you can do the other way also. You impose the detector effects on the unoscillated events and then impose the probability. So you do it in blockwise so that you can study what the effect of each block is. But the speciality of Gini is to include the most up-to-date cross-section information. So, you have a prediction for this dn mu d cos theta mu, and sorry?
Here, from the nu tau,
yeah,
if nu tau oscillates to nu mu,
yeah,
so even that contribution,
right, but there is no nu tau flux in the atmospheric neutrinos. And okay, if nu mu oscillated into nu tau and oscillated back, that is taken care of by this formula. So we don't have to worry about it. So let's see what these predictions look like. Given that delta m square is small, if L is small for vertically downgoing neutrinos, L is tens of kilometers. So the argument of sign is small. So P mu mu is essentially 1, which means that N mu down should have no suppression, and N mu up large suppression. Of course, one thing you have to see, I have a sine square, and sine square is a oscillating function. So things should go down and go up again. But the super K design is such that it's rather difficult for super K to actually observe the dip. So what they study, what super K studies is SK studied N mu as a function of E mu and N mu as a function of cos theta mu. And and looking at the oscillation probability, if E is small, the argument is large. Whereas if E is large, the argument is small. So probability is likely to differ from 1 for smaller E, whereas for larger E, it is likely to be 1. But of course, when you are studying the variation with respect to E, you are integrating over all the cos thetas. So in that sense, you don't really see that 1 over E dependence, because you are integrating over L. That sine squared is getting averaged to some value. But that average carries some effect of the E dependence. And the effect of that E dependence is that at lower energies, you see a suppression. At higher energies, you don't see a suppression. That is what that formula says as far as super K is concerned. And second thing, as I just now said, at smaller L, probability is 1. So downward going neutrinos, I don't expect to see suppression. But when L is sufficiently large, I expect to see suppression. But I am integrating over all E. So I don't directly see that sinusoidal dependence on L. But in a slightly hand waving way, I would say that I would expect maximum suppression at the largest L and no suppression, and as the L begins to increase, I will see less and less suppression, and when L becomes tens of kilometers, I don't see any suppression. So this is a roughly hand waving way of interpreting that P mu mu formula in the super K context. And now let us see what the super K results look like. Okay, here you see the double ratio. This is Kamiokande about 0.6, IMB a little lower, and these are two older experiments with, of course, very limited statistics. So you see the larger error bars and they actually don't see any discrepancy. But an older experiment called Sudan, it shows whose error bar is comparable to Kamiokande and IMB. They see actually that it is smaller. And now you look at super K. They have their events, they classify into two parts. One with energy less than GeV, other with energy greater than GeV. So that's why they say sub GeV, multi GeV. And obviously the number of events at higher energy is smaller. So you see that the multi GeV event has larger error bar compared to sub GeV. And you look at the error bar of super K compared to all the previous experiments. And now, I mean, here you can say it's okay, maybe 3 sigma, 4 sigma, whatever. But here, I would say it is some 7 or 8 sigma. So there is no doubt that this R is not 1, but definitely less than 1. Okay, come down. Yeah, keep going now. Yeah, and of course, this is the particle ID likelihood. So they built a neural network to classify an event either as electron-like or muon-like. And this is their data, and this is their Monte Carlo, assuming no oscillations. And you see that in the case of electron-like events, the Monte Carlo and the data match, but in the case of muon-like events, there is a clear deficit. So this is what rules out pure nu mu to nu e oscillation as far as atmospheric neutrinos are concerned. Okay, go down. Yeah, keep going down.
Keep going down.
Yeah, keep going down. Yeah. So this is up-down asymmetry for electron-like events and muon-like events. By the way, FC stands for fully contained and PC stands for partially contained. What is the difference between FC and PC? FC means that the charge particle is produced in the detector and it stops producing Cherenkov light while it is still in the detector. And as far as electron events are concerned, there is no subclassification FC and PC because the electrons lose their energy so quickly through Bremsstrahlung and pair production that if that event is produced in the fiducial volume, you know for a fact that such an electron cannot exit the detector. So there is no subclassification. But muon, as you all know, is minimum ionizing particle. So it can travel long distances. So if it becomes non-relativistic within the detector, stops producing the Cherenkov radiation while it is still in the detector, it is called FC. But if it goes out of the fiducial volume while still producing the Cherenkov light, it is called partially contained. And these greenish bands are the Monte Carlo expectations. 0 for electron and except this one bin, the measurements are essentially 0. But in the case of muons, again it is 0 as far as Monte Carlo is concerned, and at low energies the up-down asymmetry is 0. This is because at very low energies, and we are talking about 1/10 of GeV, at such low energies even downgoing neutrinos are oscillating. So that is why the up-down asymmetry is 0. But as you go to higher energies, the downward going neutrinos are not oscillating, but the upward going neutrinos are oscillating. So as you go to higher energies, this up-down asymmetry increases. Okay, go down. Yeah. This is the data by Monte Carlo for E-like events and mu-like events as a function of L over E. And you see that expectation is a little more than 1 and it is flat as far as E-like events is concerned. But for mu-like events it starts at 1 and as L over E increases it flattens to at 0.5. So this is another proof that it is the muon neutrinos which are oscillating, not electron neutrinos. Okay, go down. Yeah, this is in some sense the big thing about super K. They have plotted as a function of this zenith angle of the muons, and also divided electron like, muon like, then sub GeV, multi GeV. So 4 independent data sets, and sub GeV electron, the green, red is the no oscillation Monte Carlo, and then you have the data points, and they agree reasonably well both in sub GeV as well as in multi GeV. But in the case of muons, you see that there is large suppression for sort of neutrinos traveling from the other end of the earth, whereas suppression is much lower for neutrinos coming down. There is still some suppression, but it's much lower for neutrinos coming down. Whereas in the case of multi GeV, you see very large suppression for upward going neutrinos, but for neutrinos traveling even few hundred kilometers, it is essentially zero suppression. So all these features that I have pointed out, if you try to put them together you try to explain all these features using a single hypothesis, the only hypothesis which fits is that mu is oscillating into a neutrino other than nu e, and that oscillation probability is the standard oscillation probability. And then you assume the standard oscillation probability expression and do a chi-square fit, and the best fit value for delta m square, this was the first value, 0032, and the mixing angle is sin square 2 theta equal to 1. Go down. So this is the delta h square, and this is sin square 2 theta, and the best fit point is there. This is the 1 sigma, 2 sigma, and 3 sigma. Sorry. Oh, by the way, this green, it should have been 99%. Probably 95%. There is a typo here. It says 90%. But this is 1 sigma, 90%, 95% confidence level. I think it is 95%, could be 99%. Go down. Yeah, keep going down. Yeah, they have also done, here they talked about so far fully contained and partially contained events are talked about, but you can also have neutrino interactions in the surrounding rock, and muon comes in. When the muon comes in, it starts producing Cherenkov light and then stops in the detector. Those are called stopping muons. But some muons are such high energy that they actually go right through the detector. They are called through-going muons. Since these are very high energy muons, number of events is limited, but they were large enough to be able to do a statistical analysis, and they have done so. And you see that this black curve is the no oscillation hypothesis, and these blue are the data, and red is the oscillation hypothesis with these parameters, and you see that the red fits the data better than the black curve. Yeah, go down. Okay, that was, I believe, for through-going muons, and this is for stopping muons. The two are two independent data sets, so they analyze them separately. Now, so as I said, there was two possibilities, nu mu going to nu tau or nu mu going to nu sterile. But if nu mu goes to nu tau, the oscillation probability is what I wrote down. But if nu mu goes to nu sterile, then there is nu mu has a neutral current matter term, but nu sterile does not. See, in the discussing the matter term, I discussed only the so-called charge current term. The nu e interacting with electrons in the matter. But if you are talking about nu mu and nu tau, nu mu interacts with matter through neutral currents. Nu tau also interacts with matter through neutral currents as far as elastic scattering is concerned. Whereas nu sterile doesn't interact at all. So if you are talking about nu mu to nu sterile oscillations, then nu mu has the neutral current matter term and nu sterile doesn't. So I can make a distinction by looking for the effect of this matter term. If it is nu mu nu tau oscillations, I shouldn't find any effect of matter term at all. Whereas if it is nu mu nu sterile oscillations, I should find the effect of this matter term, especially in the upgoing events, and that is what is discussed here. And the zenith angle distribution. So the solid line is prediction for tau neutrinos, and the dashed line is for sterile neutrinos. At this level, actually, you can say that both hypotheses seem equally likely, but this was in 2000, but by 2001, okay, this was a paper written in 2000 based on about 2 years of data, but in 2001 I attended a conference where Super K presented their data, and with about 4 years of data, the distinction between the nu mu to nu tau oscillation versus nu mu to nu sterile, one could distinguish it. But theoretically you see that because of that neutral current matter term being missing, in the case of upward going neutrinos, there is a larger suppression if it is a nu mu to nu sterile oscillation, whereas the suppression is less if it is nu mu to nu tau oscillation. So like 100 versus 125. So if you improve statistics, certainly one can make a distinction between the two. And with the doubling of statistics that was available by 2001, one could actually disfavor the nu mu to nu sterile. And of course, by now the statistics are built so much that sterile neutrinos are, as far as atmospheric neutrinos are concerned, the deficit in atmospheric neutrinos is not due to oscillation into sterile neutrinos. There are other studies done about possibility of detecting oscillations into sterile neutrinos, but the main deficit that we see, that is due to nu mu to nu tau oscillations. Okay, go down. I think mainly this is what, okay, this is partially contained events, again sterile versus nu tau, I think. Yeah, black dots for tau and empty squares for sterile. So this is trying to make a distinction between the two hypotheses for different data set. Yeah, this is so all these features that I pointed out in this paper, you can explain by the fact that mu is oscillating into a non-electron neutrino flavor, and there is preference for mu to nu tau. The data presented in this paper doesn't quite rule out mu to nu sterile, but later data ruled that out. So based on that, one could firmly say that Super K has established, number one, beyond a shadow of doubt, that there is something going wrong in atmospheric neutrinos, because as I said, until 1996 there were people who were skeptics about atmospheric neutrino problem, but post Super K all such doubts disappeared. Not only that, Super K, based on that energy dependent suppression and also zenith angle dependent suppression, they were able to show that the only hypothesis which fits that energy dependent suppression and zenith angle dependent suppression is the oscillation of mu into a flavor other than electron.